Alright, continuing on with lecture, we have section 5.3, Associations and Categorical Variables, and our two goals are to find conditional probabilities and determine if events are dependent or independent. So an example here, two psychologists surveyed 478 children in grades 4 through 6 in elementary schools in Michigan, and they asked the students whether their primary goal is to get good grades, to be popular, or to be good at sports. So if we selected a student at random from the study, what is the probability we select the girl? To answer that, well, we can easily verify, okay, there's 251 girls, and the total number of students surveyed is 478, so there's the highlights, and this is the mathematical work. 251 divided by 478, and that equals 0.525. The next probability, selecting a girl whose goal is to be popular. So we are concerned with the probability of a girl, selecting a girl, and their goal is to be popular. So we can see that the highlights, there's their intersection, 91, out of the total 478. And here's the mathematical work, 91 divided by 478 equals 0.190. And then the probability of a student whose goal is to excel at sports. We're only concerned with probability of being excelling at sports. So we look at this column, sports, and there's 90 total that want to be excel at sports. So it's 90 divided by 478, and it equals 0.188. So if we knew the chosen person was a girl, what is the probability that the girl's goal was to excel at sports? So this is a new kind of probability called conditional probability. So computing this probability of excelling at sports given that we chose a girl, well, we only look at the girl row because we're given that we selected a girl. So our denominator will be this 251, and looking at the girl row, finding sports, it's going to be 30 divided by 251, and you can see that equals 0.120. And then our next goal is to find the probability of selecting a boy, given the goal is doing well in grades. So so we're given the goal is grades, so that it switches up here, right here. So we look at the grades column, and that's our denominator, that 247. And so our intersection for boys and the grades is 117. So we get 117 divided by 247, and it equals 0.474. So sometimes the knowledge that one event has occurred changes the probability that another event occurs. And any probability that is revised to take into account the known occurrence of other events is said to be a conditional probability. And we just computed a few of those on the previous slide. So consider a fair die being tossed, with A defined as the event 6 appears, but suppose that the die has already been tossed and B occurred, where B is the event an even number appears. Find the probability of A given B. So we can look at the set, 2, 4, and 6, those are the even numbers, and we are looking at, so we were given that there is an even number that appears, there's 3 outcomes, and we wanted to figure out that the 6 appears. So we can see that 1 out of these 3 appears, so we can compute the probability of A given B equals 1/3, and this is just saying probability of A given B, the conditional probability, has occurred. And the probability of A is just the unconditional probability of the event A, which in this case, looking at this Venn diagram, you can see 1 outcome out of the 6 possible, and that's just 1/6. And this might not be clear to you yet, but that's fine. You can ask questions in lecture meetings, conferences, or WebEx on Tuesdays and Thursdays. So probability of A given B, we're looking at the probability of sports given that we selected a girl, and we did this a couple slides ago. So we're concerned with the girl row, and there's a total of 251 divided by the, or 30 divided by the 251. Those are the two numbers that we get, equals 0.12. So this gives us more information. Given that B occurs, which girl was selected, the relevant sample space is no longer S, but consists of only outcomes in B. And then given that B has occurred, A has occurred if and only if one of the outcomes in the intersection has occurred. So going back up to here, while we can see that B occurred because there was 250 when one girls selected for the survey, and then out of the 251 girls, 30 wanted to excel at sports. So that's all that slide is saying. Another example, consider the set of families having 2 children. Assume that the 4 possible birth sequences, younger child is a boy, older child is a boy, younger child is a boy, older child is a girl, and so on. So boy, 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 girl, girl, boy, girl, girl are the 4 samples or outcomes in the sample space. So what is the probability that that both children are both boys, given that at least one is a boy? So let A be the event that both children are boys, and let B be the event that at least one child is a boy. So that's probability of A given B, and here's our sample space that I just mentioned. Boy, 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 girl, girl, boy, girl, girl. So continuing this example, A has one outcome, where the event that both children are boys, and B is the event that at least one child is a boy, and we can see that there's 3 outcomes there out of this sample space, 1, 2, and 3. And so given that B occurs, the relevant sample space includes 3 outcomes, and it satisfies the event A, and we just saw that there's 1 outcome here, 3 outcomes here, so it's probability A given B equals 1/3, or also known as probability that both children are boys, given that at least one child is a boy. It's the same probability, just restated in this example. And then we can look at this with not just with a sample space, because we can look at this as a formula, probability of A given B. Well, kind of hard to see how it equals 1/3, but we have a 1/4 chance of it being 2 boys, or both children being boys, and divided by 3/4 of the time, there's at least 1 boy, as we can see in the set B. And that just, any conditional probability is just probability of A and B divided by probability of B, or whatever's after this given sign. And looking at it closely, here it is again, the probability of A given B is probability of A and B divided by probability of B. And we can see how that relates to our survey example about girls and boys and excelling at grades, being popular, or excelling at sports. So our probability of a girl being selected is 251 divided by 478 right here. And the probability of sports and a girl occurring or being selected is 30 divided by 478. Well, the 478s cancel out, and it just equals 30 divided by 251, and that equals 0.12. Another example is transportation to class. So there was a survey asking 278 people, 124 males, 154 females, and whether they use a car to get to class, a bike, walking, or to use the bus to get to class. So we were asked, find the probability of riding the bus given that the person is female, probability of bus given female, So we're concerned with this row, so 154 females, and females, and the bus intersects right here, so just 32. 32 divided by 154 is what the probability equals. Went a little too far. So find the probability of a female riding the bus. Well, we can see that that's right there, 32 divided by 278. Notice how that's different than this. This part comes from the numerator right here, and that's just the total number of people. While finding the probability that a person that is riding the bus is female, so that's saying probability of female being selected given that we know the person rides the bus, and that's where this circle comes in because we're concerned about this bus column. The 55 is our total, and we're concerned with females riding the bus, or that's what our interest is. So 32 is our choice, or our number here, so it just equals 32 divided by 55. Another example, suppose that all individuals buying a certain digital camera, 60% include an optional memory card in their purchase, 40% include an extra battery, and 30% include both a card and a battery. Consider randomly selecting a buyer. Given that the selected individual purchased an extra battery, what is the probability that an optional card was also purchased? Well, we can look at this. So the event A is that a memory card was purchased, and the event B is the battery purchase. So we have probability of A equaling 0.6 and the probability of B equaling 0.4, and we can see how they got that up here because A is the optional memory card and 40% is the extra battery. That's where they get these numbers. And the probability that both of them purchased it was 30%. So probability both purchased equals probability of A intersection B, or probability A and B, and that equals 0.3, and we get that right up here. So we were interested, given that the selected individual purchased an extra battery, and the probability an optional card was also purchased. Well, that's the probability of a battery being purchased given, or no, probability that both were purchased given that a battery was purchased. And so using our probabilities from before, our intersection between those two events was 0.3, while our battery purchase was 0.4, and that's our denominator here, and that just simplifies to be 75%. So that is, of all those purchasing an extra battery, 75% also purchased an optional memory card. So the probability of a battery being bought given that a memory card was purchased equals the intersection that we got from earlier, the 0.3 likely. But the denominator is different because we are concerned with them buying an optional memory card, and that's 0.6, and we can see that those two probabilities don't match up. So probability of A given B does not equal probability of B given A. And here's the general multiplication rule. Rearranging the conditional probability equation, we get this rule. So the probability of A and B equals the probability of A given B times probability of B. And we also get this way too, probability of A and B equals probability of B given A times probability of A. So an example of this, an urn contains 5 white chips and 4 black chips. 2 chips are drawn sequentially and without replacement. What is the probability of obtaining the sequence white-black? So A, the white chip is drawn on the first selection, B, black chip is drawn on the second selection. Probability of A and B equals the general multiplication rule of probability of A times probability of B given A, and we know that there are 9 total chips in the urn and 5 white right here, so 5/9 times the probability of B. A black chip is drawn on the second selection, given that the white chip was drawn on the first. Since there's 8 left, and there's only 4 white chips because we selected a white chip on the first try. That's where we get this 4/8 from. Multiply these numbers and it equals simplified 5/18. So independent events. 2 events are independent if knowing that one will occur or has occurred does not change the probability that the other occurs. So 2 events A and B are said to be independent if probability of A given B equals the unconditional probability of A. If 2 events are not independent, they are said to be dependent events or are associated. Independent events. These 2 events are independent if knowing that one will occur or has occurred does not change the probability that the other occurs. Just previously said that. And we already went over this, but probability of A given B equals probability of A. It is also true that the probability of B given A equals probability of just the unconditional B. And we can look at the probability of B given A. We can see that that is just the normal conditional probability formula. So the intersection of A and B, the probability of that, over all outcomes of A, probability of A. Well, we can also replace this probability of A and B to be probability of A given B times probability of B. And that's how we rearrange that formula. And the multiplication rule for 2 events. If the 2 events A and B are independent, this is true. So it's the probability of A multiplied by the probability of B. And that's only when they're independent. That's very important. While if they're not independent, you must multiply it by the conditional probability of A given B times probability B, then equals the intersection of the 2. Not disregard that. The definition of independence: events A and B are independent if knowing A happened does not change the probability of B. So in symbols, probability A and B are independent if and only if probability of B given A equals the unconditional probability of B. Same thing, just further conditions. Equivalent formulas for independence are probability of A given B equals probability of A, and the intersection of A and B, probability of that, equals probability of A times probability of B, only when they are independent. So an example of that is 2 fair 6-sided dice are rolled. Let A equal 7 be the event that the dice sum to 7, and B be the event that the first die lands on a 4. Are A and B independent? So here's all our outcomes, and so here's all the outcomes where the total equals 7. So 6 and 1, 5 and 2, 4 and 3, 3 and 4, and so on. That's the event A, while the event B is this column. So we can see that the probability of A equals 636 because there's 6 circles here. We'll click through this. Now, that's the unconditional probabilities of probability of A and B. But if we wanted to look at the probability of A given B, well, we can see that there's an overlap of the circles, and there's 6 total outcomes because we're concerned with this column, because we're given that B equals 4 is the first event, or that the first die lands on 4. So, and there's 1, so it is independent because the unconditional probability of A equals the conditional probability of A given B. So you can see that here. Yes, they are independent. Another method, probability of A and B, well, 1 out of the total 36, where 1/36 makes sense. Well, the probability of A times probability of B, 6 times 36, 6 divided by 36 times 6 over 36 equals 1/36, and we can see that that equals the same thing, but that is not foolproof, but that is a much easier way to figure it out than trying to manipulate the conditional probability formula. And yes, the 2 events are independent. So 55% of all students at the university are female, and 30% of all of the students at the university are graduate in 4 years. 13% of all students at the university are women who graduate in 4 years. Are gender and graduating in 4 years independent? So using the notation, we write the probabilities that we know. F, female, G, graduate in 4 years. Probability of F is 0.55 up from up here. And probability of G, graduating in 4 years, is just this 0.3. And the intersection of those both is 13%, because we were told of all the students at the university are women who graduate in 4 years, 0.13. So if we would multiply these unconditional probabilities, you can see that it does not equal this. So since they are not equal, gender and graduating in 4 years are not independent, so they are associated or dependent. And another example, let A be the event of drawing a king from a standard poker deck, and B the event of drawing a diamond. Are A and B independent? So here's all the total outcomes. So the probability of A, there's 4 kings in a standard deck, and there's 52 total cards. That's where we get the 1/13th. And B, the event of drawing a diamond, well, 1/4 of the deck are diamonds, and 13 out of 52, or not, this is wrong. That should be 1/4. So you can see it's right down here. The probability of A and B equals 1/52nd, and that makes sense. Drawing a king, that's a diamond, is 1/52nd. So the intersection of the two we see was equal to 1/52nd because there's only one diamond king. So these unconditional probabilities, which this one should be 1/4, 1/4 times 1/13th is equal to this 1/52nd. So we conclude that A and B are independent because it equals the product of these unconditional probabilities. Another example, gender of babies. Suppose 49% of babies born in the U.S. are girls. A couple has 2 children. Find probability that both are girls. Since the events first is a girl and second is a girl are independent, then we can use this formula. The multiplication of the unconditional probabilities equals the intersection of those 2 probabilities. So we know that 49% of the babies born are girls, so that's our first is a girl times Again, the second is a girl because they're independent, and 49% of babies born are uh, girls. So therefore, we can multiply these, and it equals this 0.24. And another fun example, according to a Wall Street Journal survey, 70% of consumers prefer to shop online rather than in person at their favorite retailer. Suppose 3 consumers are randomly selected with replacement from a population of consumers. What is the probability that all 3 prefer to shop online? What is the probability that none prefer to shop online? And what is the probability that at least one prefers to shop online? So the first one, probability of all 3 prefer to shop online, well, that's just the probability that the first prefers to shop online, and the second prefers to shop online, and the third prefers to shop online. Well, these are independent events because one consumer's answer will not affect the probability of the next consumer's answer, so we can use that multiplication rule. So 0.7 times 0.7 times 0.7, that equals 0.343. And then our second problem was, what is the probability that none prefer to shop? Well, we can use the unconditional probability or the complement that they prefer to shop online, which is 0.3 right here. So that's also the same thing, where the first does not prefer to shop online, and the second does not prefer to shop online, and the third does not prefer to shop online. Well, that's just a multiplication of 0.3 right here for this probability, 0.3 right here for this probability, and 0.3 again for this third part of it, and that is equal to 0.27. And you can see how that's different than why that's different from just subtracting this from 1, because that doesn't really, because we'll talk about that. So the third part of that last example, we are looking at the probability of at least one prefers online. Well, we just computed that none of them prefer online. Well, to figure that out, at least one of them prefers to shop online. We can use the complement rule, and that's 1 minus our previous probability, and that's 1 minus 0.027, and that equals 0.973. So at least one type probabilities. Sometimes we need to find the probability that an event occurs at least once in several independent trials. The easiest way to calculate these probabilities is by finding the probability of the complement, which we did on the previous example. Remember that the complement of at least one event occurs is no events occurring. See how that's different? To compute the probability that an event occurs at least once, find the probability that it does not occur at all, and subtract it from 1. So our last example here, cell phones and surveys, a 2010 study conducted by the National Center for Health Statistics found that 25% of U.S. households had no landline service. This raises concerns about the accuracy of certain surveys as they depend on random digit dialing to households via landlines. We're going to pick 5 U.S. households at randoms. What is the probability that all 5 of them have a landline? Well, we can assume by it that these people aren't interacting with each other, so we would just multiply, it would be 0.75 to the 5th power, and we can see that on the next slide. The second, what is the probability that at least one of them does not have a landline? Well, that would be finding the probability of we would want to find the probability that all of them have a landline, and 1 minus that is right here. 1 minus, I talked about the 0.75 being raised to the 5th power. That equals 0.763. And then the probability of at least one of them does have a landline, well, we would find the probability of no landlines, and that's 0.25 to the fifth power, right here. And then 1 minus that equals around 0.999. And that is it for Chapter 5. If you have any questions, please email me or attend office hours or the WebEx lectures.